Welcome to The Explainer. I am absolutely thrilled to have you here for what I really consider to be one of the most fascinating engineering challenges of our modern world. Okay, let's dive into this. Today, we're unpacking the invisible nervous system that keeps literally millions of tons of steel moving safely at high speeds every single day. We're talking about railway transmission systems. We'll be looking at exactly how data is structured and moved across these massive bare networks, and, why the technologies they choose to rely on might actually surprise you. Think of this as our syllabus for today's masterclass. We'll start with the railway data backbone, then define transmission systems, explain circuit switch networks, look at why railways prefer SDH, discuss the inefficiency of locked paths, and finally, weigh balancing safety and efficiency. All right, part one, the railway data backbone, moving critical information. So unlike an office building or a factory where all your computers are clustered together in a nice tight little radius, railway operations are exceptionally long and thin. We're talking about systems stretching across hundreds or even thousands of miles of track. Which brings us to the ultimate engineering challenge. How does critical safety data travel those miles without ever getting lost or delayed? Just imagine a central control room needing to immediately stop a train because there's a hazard ahead. That digital stop command, it has to travel through miles of cables, nodes, and base stations, and it absolutely cannot afford a single millisecond of delay. Nor can it just be drops because, oops, the network got too busy. Solving this massive problem requires highly structured data environments. Let's move to part two and see how this builds, defining transmission systems, managing the network. By definition, transmission systems are the hardware and software elements that manage the communication process and the use of the transmission path over long distances. It's actually really crucial to understand that we aren't just talking about laying a single copper wire or a fiber optic cable on the ground and calling it a day. No, the transmission system is the intelligent architecture layered right on top of those cables. It dictates exactly how your data is translated, packaged, prioritized, and moved. Without these highly managed layers, a physical cable would just get completely overwhelmed by the sheer volume of voice, data, and safety commands all trying to cross it at the exact same time. Now, what's really interesting about this is the layered hierarchy here. Take a look right at the top in that core SDH transport box. That is where the highest bandwidth, most absolutely crucial services are managed. As we move down the diagram through the access layers and primary layers, the bandwidth scales down to sub-2 megabit services, all the way down to the basic copper layer at the bottom, handling your simple analog services. This structure ensures that everything, from a basic line-side telephone to a massive high-speed data stream, has a very defined, heavily managed place in the ecosystem. Moving on to Section 3, Circuit Switched Networks Explained, PDH and SDH. The defining characteristic of these older legacy architectures is a permanent connection established between two applications. Read that again, a permanent connection. This is fundamentally different from how your internet works at home. The internet uses packet switching, right? It chops your data up, sends the little packets scattering across a dozen different routes, and basically hopes they all reassemble at the end. Circuit switch transmission doesn't do that. It draws a rigid, unbending, and completely permanent line straight from point A to point B. Think of this process like creating a dedicated VIP lane on a really busy highway. Step 1, the application initiates the connection. Step 2, hardware devices called multiplexers literally carve out and allocate specific time slots for this data. So for example, in an E1 data stream, there are 32 distinct time slots, and specific slots are dedicated purely to one conversation. And then step 3, that permanent, dedicated path is locked between the nodes. Absolutely no other traffic is allowed to enter this VIP lane. It's reserved strictly for that specific application's data, period. And this brilliantly illustrates exactly how that works in practice. On the left, we have a concentrator or telephone. It feeds into a primary multiplexer, which physically and logically locks in that dedicated VIP lane across the transmission nodes via the fiber cable directly to the junction boxes and the receiver over there on the right. Once this path is established, it's pretty much as if a solid, unbreakable pipe has been constructed between those two end users.
Which brings us to Section 4, why railways prefer SDH. Guaranteeing high availability. Let's examine how this functions in practice. Why would a modern high-tech railway rely on this rigid type of network?
Why not just use the dynamic internet protocols we use for literally everything else? Well, the answer comes down to one single word: dependability. SDH is essential because it actively reserves dedicated bandwidth. By creating that VIP lane we just talked about, it guarantees high availability for the backbone. It enforces strict independence between different systems. In a railway environment, an emergency braking command simply cannot afford to wait in a network queue behind some passenger's Wi-Fi request or a routine diagnostic report. By keeping these systems completely independent, SDH prevents safety-critical data from ever being overloaded by background traffic.
So the crucial point is this: the degree of independence that SDH offers makes the system virtually bulletproof against data collisions and congestion. You always know exactly how much bandwidth is available, and you know exactly how long a signal will take to arrive, simply because the path is perfectly clear, 100% of the time. It is total safety and immediate performance.
This brings us to the primary limitation of the system, Section 5, the inefficiency of locked paths, the cost of the VIP lane.
Let's objectively compare our circuit-switched SDH networks against modern packet-switched IP networks. SDH relies on permanent connections, dedicated bandwidth, and a locked resource. Conversely, IP networks use shared capacity, dynamic routing, and best effort delivery. IP networks are honestly brilliant at sharing space. If one application isn't transmitting, another application just instantly borrows that bandwidth. However, IP only promises best effort delivery. There is no absolute guarantee that those packets will arrive in order or exactly on time. SDH, on the other hand, stubbornly holds onto its resources no matter what.
And that leads directly to its fundamental flaw. Because the transmission path is completely locked up, it remains locked even when absolutely no data is being sent. Returning to our VIP lane analogy for a second, yes, the VIP lane guarantees a fast, uninterrupted trip when the VIP is actually driving. But for the remaining 99% of the day, when the VIP is sitting at home, that lane sits entirely empty. Meanwhile, thousands of other cars are jammed up in the regular lanes, forbidden from using the empty VIP lane. That is an immense, almost mind-boggling waste of overall network capacity.
Section 6. Balancing safety and efficiency, the engineering trade-off.
So here's the ultimate engineering trade-off. On one hand, SDH ensures critical commands are never delayed. It's bulletproof. On the other hand, SDH wastes immense network capacity, keeping those idle communication paths open. Now we have newer IP networks that are vastly more efficient, but they only offer that best effort delivery model. And in the world of rail engineering, where human lives are quite literally on the line every second of every day, best effort has historically just not been acceptable for safety-critical systems. So engineers are essentially paying a massive premium in network inefficiency, strictly to buy absolute peace of mind.
Which leaves us with a really compelling question for the future. As trains become increasingly data-centric, requiring live video feeds, real-time telemetry, continuous tracking, can the future of rail afford to remain this inefficient in the name of safety? Or will the ongoing evolutions in networking technology finally provide a way to guarantee absolute, fail-safe delivery while simultaneously maximizing our bandwidth? It's a profound challenge, and the answer to that question will likely define the next generation of global transit. Thank you for joining me to explore this incredibly complex web of railway engineering. I really hope you walk away with a greater appreciation for the hidden signals keeping us all on track.